So I was just telling what is tropical geometry about. And you can think of it as a toolbox to transfer polynomial equations and their solutions, algebraic varieties, into polyhedral fans and graphs. But at the same time, you want to do this like in a way that you preserve the, the algebraic information about the original variety, okay? And then here I showed you like an example of a degree 2 polynomial in variables x and y that, the variety can be translated to this a polyhedral object, and its combinatorial shadow on a plane is just the graph. And then I'm going to explain to you later, how to obtain these polyhedral pictures. Okay, good. So here is the outline of my lectures. So first I'm going to talk about tropical polynomials. And for example, here, you would see the pictures that would show up like during this talk. And then I'm going to show you like, what sort of like information we can obtain from tropicalization of polynomials. So we would see the algebraic part, somehow the combinatorial part, and somehow like the relation with subdivisions of certain polytopes. Okay, so the second lecture is going to be devoted on tropical varieties and then how we translate tropical varieties over arbitrary fields to some polyhedral complexes and what sort of properties these complexes would have. So here is an example again of a tropical variety. And we will see like fundamental theorem and structure theorem in tropical geometry. So the third talk would be related to tropical linear vector spaces. We start from arbitrary linear vector space, and then we see how to tropicalize it. And especially this family of, tropical varieties have many nice properties, and they are related to subdivisions of matroids and also has applications like in phylogenetics that I would briefly talk about. Okay, and this was just a slide showing you like an outline of the talk, and I'm going to now start to give you like a more concrete definitions of tropical geometry and what properties we would see during this talk. Okay, so what is tropical geometry about? So you can think of tropical geometry as a new sort of algebraic geometry. Like in algebraic geometry, we are interested like in polynomial equations and their solution space, right? So here, so we would do the same, but we want to see, when you want to do like algebra, you want to look at the polynomials and the solution space of the polynomial. Here is just the same, but we want to change the solution space. And instead of looking at the solutions like, real solutions or complex solutions, we're going to look at the solutions over so-called tropical semi-rings. Okay, so here is an example, just to give you like an idea of what we will see later. So start from a polynomial in two variables, x and y. So that's a degree 3 polynomials, y squared minus x cubed plus 3x squared minus 2x. Okay, so and then we are interested like in the solution of this polynomial. So we can, like in algebraic geometry, you can choose what field you wanna work on. For example, if I want to look at the solution over real numbers, only real solutions, so then the graph of this polynomial, so this solution space, looks like the picture that I have on the left. Okay, so that's a real curve. And then if I want to look at the complex solution, so then I would get this torus like in the middle with, when I remove one point. And then like in the tropical world, so I would look at the solutions over tropical numbers that I'm going to define like in my next slide. And the picture that we would see is the one on the right. Okay, so which looks like a graph, right? But at the same time, as we saw before, so this graph is going to have to encode lots of algebraic properties of the original variety. So one such example would be the dimension. So this is a curve like dimension 1 curve, the plane curve. So you see that my other picture is also the tropical curve has been also drawn like on the plane. Okay, so it has the same dimension. So it has the same degree. So by degree, I mean, when you want to compute the degree, you would take, if you're like in the plane, you would take like an arbitrary line, and then you would intersect it with the curve, with the real curve here. So if you do this here, so then you see that, it would intersect like 3 points, like in my real curve. So that's the degree 3 curve. And if you look at the tropical picture here, you would see that in the tropical picture, so there are 3 rays pointing upwards, 3 rays, to the right, and 3 rays like here. So the number of these rays that you see is also equal to the degree of my variety. So there are some information that would be translated to the tropical world. And another thing is that this picture, this real picture, so this polynomial and the corresponding variety has genus 1, meaning that, if I look at this real picture, I see one circle somehow encoding this genus information. Look in the torus, I see this one hole here, one-dimensional hole. So that would be the genus of my of this curve again. And then if I look at the tropical picture, again, I see like just one cycle like in the middle, which tells me what is the genus of my tropical line. So you see some of these algebraic invariants would be translated to the tropical world. And basically we can, instead of studying the geometric information of this curve, so I would take the somehow like the tropical one, which is in the combinatorial world, and would study the invariance of this curve. Okay, so is there any questions so far? Okay, so now let me formally define what do we mean by tropical numbers or tropical arithmetic. So as we saw before, tropical geometry is algebraic geometry over the tropical semi-ring. Like, algebraic geometry could be over, usually it's over complex number. Here we're gonna take algebraic geometry over tropical semi-ring. And by tropical semi-ring, I mean, you take like all the real numbers and then you add the infinity to it. And then you define like the tropical addition and tropical multiplication like in a new way, that the tropical addition is going to be the minimum of 2 numbers, minimum of x and y, and the tropical multiplication is going to be the sum of 2 numbers. So you just change the notion of addition and multiplication in the usual arithmetic to minimum and the summation. Okay, so here's an example. So if I take 3 and 4, and then I multiply them, tropical multiplication, I consider like the tropical multiplication of these 2 numbers. So that means I have to sum them up. So I get 3 plus 4, which is 7. And then if I consider their tropical sum, so then that means I need to take the minimum, which would be 3. Okay. And I would like to pause here for maybe for 30 seconds and then ask you guys to think about it and then tell me what is the, what would be this number in the tropical world. So that would be 3 tropical multiplication with the 4, the tropical sum, and 4 and 8. And then maybe you can, write your answers like in the chat. And then if you get enough answers, someone tells me, and then I stop, and then I continue. Okay. Okay, I don't see the chat, but if there are maybe answers, maybe Tony can tell me, or Christoph.
There is a question in the chat. Should we think of infinity as plus or minus infinity, or plus infinity, or neither?
Plus infinity. So by infinity, I mean just plus infinity. Yes. Oh, I see. I can see the chat actually. Yes, perfect. Okay, perfect. So it seems like 7 is the answer. You take the tropical sum of 4 and 8, and what you get is, the minimum, which is 4. And then you take the tropical multiplication with 3, that would be the usual sum, and then you get 3 plus 4, which is 7. Okay, perfect. So now, okay, and now we're gonna think about these, we're going to take this plus infinity and then take the sum, the tropical sum of plus infinity and every other number, because we're going to take the minimum. You see that, you're always going to get this smaller number x. So that means this is somehow like the additive identity, like in the tropical world. Okay, so my tropical semi-ring has an additive identity, which is the plus infinity. And then the second one, how about the tropical multiplication, the identity for the multiplication? Again, look, there's a question mark here, meaning that you do the computation. So what number should I put here that whenever I multiply it with every other number, so I get the same number back? Okay, so that means the sum should be x, right? So that means the tropical the tropical multiplication identity is just 0. Okay, perfect. Thank you. And then the third, the third arithmetic question is that we have 2 and 8, and then I want to find like a number here that 2 plus tropical sum x is just 8. Okay, and then you see that this number doesn't exist, because then I have to take the minimum of 2 and some other number and get 8 back, right? Which is not possible. So that just tells me that there is no subtraction here. So like 8 minus 2 doesn't exist. Okay, so that's why it's not a ring, so it's a semi-ring. But you see that, if you do this example again, you see that it's associative with additive and multiplicative identities. Okay, is there any question here? Now you can see the chat, so please feel free to add your questions. Okay, so now how about the tropical polynomial? So they're the first objects to look into when we want to do like algebraic geometry over these new semi-rings. So a tropical polynomial is going to be a piecewise linear function with integer slopes and a finite number of linear pieces. So what do I mean by tropical polynomial? So I just take a polynomial in which the sum has been replaced, the usual sum by the tropical sum, and the usual multiplication with the tropical multiplication. Okay, so now my polynomial was x4 plus 2x plus 4, and I have replaced this tropical and the tropical sum and multiplication. So that means I have 3 terms, right? My polynomial has 3 terms, x to the 4th, 2x, and 4. And if you do this tropical arithmetic, so you need to take the minimum of these 3 terms. So the first one, x to the 4, is like x times x times x times x, which in the tropical world is going to be 4x, right? The second one is 2 times x, which is going to be 2 plus x and 4. So the way that you can draw the graph of this polynomial is to, for example, what I've done here is to draw the curve of each of them and then take their minimum. Okay, so I have drawn the for example, the y equal to 4x. So that's my blue line here. So just plug in the number, right? And then you have 2 plus x, and then you have y equal to 4. Okay, you see these 3 curves here. And then I need to, in order to draw the tropical lines, I have to take their minimum. For example, if I'm here, so like in this area, so the minimum of these 3 lines would be just this green part. If I'm here, so I get this, the red part of the curve, y equal to x plus 2. And then here I get the part corresponding to y equal to 4x. So my tropical picture is going to look like this black curve that I have drawn here, which, as you see, so that's a piecewise linear function. So that means, there's like a bunch of broken lines here, like in the picture, right? Okay. So this is how we would look at the tropical polynomials, right? So we start from polynomials, like usual polynomials, and then you can replace sum and multiplication with the tropical sum and tropical multiplication. And then you just need to take the minimum of bunch of, linear functions. Okay, perfect. So the how about the variety of this polynomial or the solution set of these polynomials, right? So now I want to generalize the example that you just saw before. So you take, let's take a like an arbitrary polynomial in n variables x1 to xn, okay? And the coefficients of my polynomials are coming from these tropical semi-ring. So that was just real number with infinity. So I'm allowing to have infinity plus infinity like as a coefficient. So now the tropical hypersurface or corresponding variety would be just, you can define it just to be the set of all those vectors like in Rn, all those real vectors, such that either when I plug in these numbers, so what I get is infinity, f of w is infinity, or the minimum of fw is achieved at least twice. Okay, so let's see what it means here. Like again, like in an example. So let's take this polynomial f, which is x plus y plus 0. Okay, so again, you know, I have my polynomial has 3 terms, like x, y, 0, and I'm going to take their minimum. Okay, so how can we draw this curve? Again, we are looking at, you know, I said like the minimum is going to be either like to draw this curve. So either you have to look at all those weights, all those vectors such that the f of w is achieved at least twice, or those points that their, you know, their evaluation would be infinity. So these points are easy, right? Because I would get infinity. This minimum is going to be, sorry, what I'm saying here. Okay, so let me just first like tell you like what are these guys. Okay, so if I take so I'm saying like what are the values here, right? So if I take x, if I look at the points that x is equal to y, so in order to achieve this minimum twice, I either have to have like this x to be equal to y and to be larger than 0, sorry, to be smaller than 0, right? Because I want to take the minimum twice. So either I have to have x equal to y and less than 0, which is here, like, you know, when x and y are both negative on the negative side, or I have to have x equal to be 0, but again, less than y, x equal to x equal to 0 and y less than 0, or I have to have y equal to 0 and less than x, right? So this is the picture that I have drawn here. And what are these values that I have here? For example, if I take, you know, if I'm here, meaning that my x is positive and my y is positive, so then this minimum would be just 0, right? And then if I'm here, meaning that my x is negative, and my y is positive, so then I would get just x. And the same way, you know, when I look at the other orthont in this picture. Okay, so this picture is actually tropical line and somehow like the easiest tropical polynomial that you would get, tropical variety that you would get, which is the x plus y plus 0. Okay, good. So is there any question here?
I just had a question about the last line.
Oh, okay, sorry, forgot that. Yes, that's a good question. So I wanted to say, what are the values of, you know, I looked at this VF, the tropical hypersurface, and I said either the minimum should be attained twice, or the evaluation should be infinity. Okay, so I look at the evaluation, and then I put infinity plus 0 plus 0. I just made myself confused. Okay, maybe for now, you just ignore this last line, okay? And then here, what I would like to have is that, you know, I want to have these 2 points also like in my variety. So that's all I would like to have. Okay, so I would like to have all those points that their minimum is achieved twice, plus the point 0, infinity, and infinity 0. Okay, does it make sense?
Yes, thanks.
Okay, sure, yeah. So this is just to include the somehow like, you know, the infinity points like in this picture. Okay, okay, good. So, okay, now maybe you can again like think about it like for 1 minute. I'm going to pause here and ask you to try to draw the tropical hypersurface, which is the variety of this polynomial. So I have a tropical polynomial, which is 3 times x cubed plus 2 times xy. Okay, so again, so my polynomial has 2 terms, right? I'm going to draw the variety of this polynomial, and then going back to this picture. So just ignore the first part, the f of w is infinity, and then look at all those points that when I, when I compute the tropical, when I compute this tropicalization, the minimum of these 2 terms is achieved twice. Okay, and then maybe you can share your answers like in 1 minute. And then if there is any question, please let me know like in the meantime. Okay, just to make sure we are on the same page. So we are first going to look at this polynomial and translate it to some piecewise linear functions, right? To some linear functions. So like each, because I have 2 terms, so I'm going to look at the minimum of 2 linear functions, right? So the first one would be 3 plus 3x. And the second one is going to be 2 plus x plus y. And we are going to take the minimum of these 2 linear functions. We're going to look at those points that the minimum of these 2 linear function is attained twice. Okay, do we see like how it looks like? Okay, perfect.
I have a quick question.
Yes,
so when you
please.
say the minimum is attained twice, are we saying that we just want, I guess, 2 of these parameters in the minimizing function to both achieve the minimum? Or are we saying that we want 2 different inputs to these variables that achieve the same minimum value?
No, we want 2 terms of this polynomial to, to have the minimum value.
Okay, I see. Thanks.
Does it make sense? Yeah.
Yeah, that makes sense.
Okay, perfect. Yes. So for now, I would like to tell you, just forget about the infinity. So that's the answer to this question, infinity, infinity. Okay, which is correct, by the way. So this is also here. Okay, so what is this minimum? So again, we have 2 linear functions now, and then we are looking at those points that this minimum is attained twice, right? Meaning that we want them to be equal, right? If you want to have the minimum to be seen twice, you want these 2 linear functions to be equal. And then if you solve this equation, you see that this is just the equation of a usual line, right? So y equal to 2x plus 1. And that's actually why, so maybe going back to the previous slide, so that's actually why this 0 is important here, right? So if I had just x plus y, so then all I would get was this line x equal to y. And then I wouldn't see these 2 rays, right? So this 0 is not like the usual, in the usual sense that I can remove it from my picture. Okay, good. So these are the tropical lines. We just saw tropical lines and how to draw their corresponding hypersurface. So and then here is another example that you can maybe try later, that I start from a polynomial which has 1, 2, 3, 4, 5, 6 terms, right? So the first term is 1. So this is 1 times x to the 0, y to the 0. So the second term is 0 times x. Again, that would be translated to 0 plus x. And to draw the corresponding hypersurface, you want to take the minimum of these 3 linear functions, the minimum of 1, x, y, x plus y, 2x plus 1, and 2y plus 1. And then if you do this computation, that's the picture that you would see like in the middle. But looking at this graph, you see that, this variety of f has some combinatorial properties, right? For example, you like in a usual graph theory sense, Is this double minimum variety just an example, or is it important in tropical geometry? No, this double minimum, if you mean the definition of the variety, so that's, that's like for general, right? So we always define the variety of F to be those points that the minimum is achieved twice. I'm not sure if I understand the question though. Yeah, this is important because that's the definition of the variety, right? Okay, so if I look at this tropical picture that I've just drawn for this polynomial, for this tropical polynomial, now what I see is that, like as a graph, and so this picture has four vertices, like 9 edges that you can see. And also this graph somehow like divides my plane into 6 connected components, right? So by connected components, I mean, this is like one connected component, this is another connected components, etc. Okay, and then I would like to translate these sort of like combinatorial data into some polytope. So that's what we are going to do now. So how do we do this translation? So here is the answer, and I'm going to tell you, how to get to this polytope. So the corresponding polytope of this picture is going to be such a subdivided polytope. So that if you take this small triangle as a triangle which has every edge has length 1, it's like a unit triangle. So then whenever you have a polynomial of degree d, so here the degree of my polynomial is 2 because the highest exponent of the variables that I see is 2. Okay, so whenever my degree of polynomial is 2, so this polytope is going to be like a triangle of length d, such that every edge has length d. So here in this picture, so my polynomial is of degree 2, and this corresponding polytope is a 2 times, this small triangle. Okay.
You're muted.
Hello, hi.
I don't know. We lost your presentation.
Yes, by some reason I was disconnected.
Oh.
Okay. No, I'm not okay yet, right?
Not up yet. Okay.
Okay, now. Okay, I don't know what is the problem because I'm at the university and it seems I have a good connection, but it's good. You see my slide number 13, right?
Yes.
Okay, perfect. So I was just saying that, you have this tropical curve, right, of this polynomial, and then corresponding to this graph. So we have a polytope whose combinatorial data is similar to the graph. So like in a sense that, there is a notion of duality going on. So like my polynomial here, my graph here has 4 vertices, 9 edges, and 6 connected components like of dimension 2. And this graph that I see here has similar properties, but in a dual sense, in a way that, the vertices here, the vertices of this graph are corresponding to the maximal cells of my polytope, which has, 4 two-dimensional cells. And the edges of my tropical curve are going to be corresponding to the edges of this picture. And the 6 connected components are corresponding to the 6 vertices like here. And the vertices are these guys. Okay, and to see this duality, we actually, I just showed you that if you look at the vertices of this graph, you see that these vertices are corresponding to the regions of this polytope, and you just put these vertices and then draw the tropical line here, which would be this guy. Okay, so there is an algorithm to get from tropical picture that we have here to this subdivided polytope that I'm going to show you now. Is there any question so far? Okay, let me open the chat here. Okay, so if not, so then I'm going to show you, how to start from a polynomial. So we already saw that if you start from a polynomial, you can draw its corresponding, variety by looking at all those points, such that when you evaluate those points, so the minimum among these terms is achieved at least twice, right? So then we obtain this curve, and then we're gonna see how to get from this curve to this subdivided polytope. Okay. So to do this, so we are going to construct a Newton polytope of any polynomial. So you start from a tropical polynomial, which is the sum of bunch of monomials here, right? The tropical sum. And each term in my polynomial is of form AU times XU. So U is a vector in U is a vector in Rn, or if you want to take the rational exponent, so that's also allowed, or like the exponent in, let's say, n numbers, like, so by XU, I mean like XU1 times XU2 times XUn. Okay, so that's my monomial, and that's a coefficient of this monomial AU. So now, because I have these many terms, so the tropical sums, if I want to translate it to the usual arithmetic, so then that means I have to take the minimum over all those or all these lines, right? All these linear functions, so that this term would be translated to AU plus, because I have x to the U1, so that would be U1x plus UNX, right? So these are each of these terms, and I'm going to take the minimum among them. Okay, and then we are going to define the support of this polynomial. The support is going to be all those exponents such that the corresponding coefficient is not infinity. Okay, so you take all these exponents U1 to UN, and then you plug it in, as they are just vectors, like in Rn, you plug them in, and then you take the convex hull of all those points. So here, let me just show you, like in an example, that, I have a polynomial with 6 terms, right? So what is the corresponding Newton polytope? So this is the point 1, which is 0, 0. Right? The corresponding monomial is like 1 times x to the 0, y to the 0, right? So that would be corresponding to 0, 0. So then I have the term x, whose exponent is 1, 0, 0, 1, 1, 1, 2, 0, and 0, 2. Okay, so that would give me this polytope as a convex hull. And then I'm going to define, somehow like lift this Newton polytope based on the coefficients of these terms in the polynomial. So whenever I see the coefficient AU, so I want to lift this Newton polytope, instead of Rn, I'm going to go to Rn plus 1, such that every point has been lifted 1 dimension higher by adding, this coefficient as the last entry. Okay, so these U, again, like these U's are the exponent and the vertices in my Newton polytope, and then I'm going to add 1 extra component, 1 extra entry to go to the n plus 1 dimensional space. Okay, so we go 1 dimension higher, and then we get like a polytope upstairs, and then we project it back to the original space Rn, and those facets that we see, those maximal faces that we see from below, so they're actually giving me sort of subdivision of this big polytope that we saw before. Okay, so let me explain this like in an example. Okay, so again, we start from this polynomial, and then we plugged in the exponent vectors, which was 0, 0, etc., right? So that was the Newton polytope that we obtained. And then now we are looking at the coefficients of each term. For example, the coefficient 1 is the coefficient corresponding to these points 0, 0, right? So I'm going to lift this point up based on the coefficients that they have. So the corresponding point here, so we go to R3, like instead of R2. So the corresponding vertex of 0, 0 now would be 0, 0, 1. And for the other guy, 0, 2, 1, 2, 0, 1. But there are 3 terms with 0 coefficients, so they would stay the same. Okay, and now I'm going to take these new vertices with those that they haven't been changed and take their convex hull. Okay, so then that would be the polytope that I would see like in a 3-dimensional space. But if we now just, punch it back to the original polytope, so we push it like downstairs, so that would induce us like a, this subdivision of the original polytope, right? Which would be this picture. And the idea is that, this is called like the dual picture of the curve and tropical curve that I had before. And the idea is to relate the combinatorics of this polytope, of this subdivided polytope, to the algebraic properties of the tropical curve that I've seen before. Okay, so please ask me a question. I think I was too fast here.
Could you go back to the previous slide for a moment?
Yes, here or the one before?
Yes, this one.
Yes. So what I mean here is that, I just lifted up these points, right? And then I took, so these guys have been now changed to these new points, right? And then I take the convex hull of these guys and the original, these 3 ones with the 0 coefficients. So it's a 3-dimensional polytope. And then the way that you can see this subdivision is you just mark the lower faces. So that would be one facet that I see below, right? And that would translate, if I project it back to R2, so that would translate to this triangle, right? And then if I look at this facet, which is again like a lower facet, that would translate to this triangle. And then the same goes with this triangle upstairs would be translated to this face here. So that would give me like a subdivision of the original triangle that I had. Is that okay?
Yes, thanks.
Mm-hmm. Okay, perfect. So there is another question. An element of the support is an ordered pair of the exponents for x and y in each term. Yes, that's correct. So I just encode the exponent vector here, right? So the exponent of x is 1, the exponent of y is 0. And then I record the vector 1, 0 for this monomial as its exponent, right? So that's just the exponent vector. Okay, perfect. So, okay, so we got back to this picture that we had this tropical curve, and then we obtain this subdivided polytope. And the idea is that their combinatorial structures are the same. The invariance that they encode is similar. Okay, so what sort of information can we get from this dual picture? So now here I would like to show you that, this observation, this combinatorial observation that we had, which was quite simple, going from, from a tropical line, from such a picture to this dual polytope, has many nice applications, like in classical algebraic geometry and tropical algebraic geometry. So namely, let me first tell you like the classical version of the theorem. So by that, I mean the statement coming from algebraic geometry, and the tropical version, which would be more combinatorial using this sort of like polytope. Okay, so the idea is that usually here you would take, like a classical theorem, and then you would try to find like a combinatorial analog of that theorem, which encodes the same information. So the classical version of this theorem that I'm going to talk about is that, if you start from a planar curve, so that means like a curve defined by polynomial of degree d, like in 2 variables, x and y. Okay, So you take such a polynomial and such a curve. So the genus of this curve, which is just a number of topological holes that you would see if you draw it like in the complex number. So this genus is going to be equal to d minus 1 times d minus 2 divided by 2. Okay, so here, this is the picture of the curve that I had before. So that's the degree 3 curve. And then you see that, that's a torus with one topological hole. Okay, so if I plug in, so my d is 3, so the degree of my polynomial was 3. So if I plug in 3 here, so I would get 3 minus 1 times 3 minus 2 divided by 2, which is 1. So at least it's correct, like in this example, you see, right? And the corresponding, I had a polynomial of degree 3, so I computed the tropicalization by replacing plus with the tropical sum, multiplication with the tropical multiplication, and then I draw the corresponding tropical curve. So I got the one in the middle. And here is just the polytope, the subdivided polytope that we just saw like in the previous slide, that here, my polynomial was of degree 3. So I would take 3 copies of this small triangle. And this is my, my 3 times a small triangle. And then I lift up every point depending on the coefficient of the polynomial that I got, and I would get such a subdivided picture. Okay, and it turns out that, the number, if you look at this polytope and the number of vertices like in the interior of this subdivided polytope, which is just 1, like encoded by this red vertex. So what you would see is this number encodes the genus of the original curve. Okay, when we do the subdivision calculation, do we always get a triangulation, or can there be non-triangle cells? So this is a very good question. No, this is just a subdivision, meaning that, this polytope would be subdivided and you might get some facets, some faces that are not triangle. You will see it actually in the next slide. Okay, so now the question is, what is the combinatorial analog of this classical version? The combinatorial, and by that I mean, what is the genus of a tropical planar curve? And they just show you here that it turns out that this interior, the number of these interior points is going to be equal to the genus of the curve that you are interested to study. Okay, and this was just one example that how we would use these sort of like combinatorial picture to read algebraic invariance of the original variety. Okay, and that's the statement that I just told you, that the genus is the number of vertices in the dual subdivision, which are in the interior of this polytope. And if every interior point actually shows up like as a vertex, in a sense, it's connected to a triangle or face here. So then this number that we read like as a genus is going to be exactly the classical one, which was d minus 1 times d minus 2 divided by 2. Okay, perfect. So is there any question here?
I didn't understand the last sentence. If each interior point occurs as a vertex in the subdivision, so what's a non-example of that?
The non-example would be, for example, if I don't have, if in my subdivision, I only have this triangle here and maybe this triangle here, but none of these four. So
the red dot exists, but there's none of those edges are there?
Yeah, exactly. So this one, like instead of 4 triangles like in the middle that they're attached to this red point, so I wouldn't get, so I would just get like this square, this parallelogram.
How could you get a vertex in the projection of a convex hull that does not connect to edges?
Well, I don't mean in the projection of the convex hull. This is just the, this is just my polytope 3 times this triangle, intersection with Z2, intersection with all lattice points. So this point doesn't exist.
This is not the dual construction you showed us with the projection?
No, this is, this is the dual, this is the same picture. You're right.
So in that picture, every vertex has to have edges.
No, but these are the, no, there were the vertices like in the boundary that should have edges, like in the Newton polytope, right? So that was the convex hull of the boundary vertices. So for example, if I don't, let's say this is 0, 0, this is 0, 0, 1, 0,
Oh,
and this
I
one is
understand.
1.
Okay. I think I.
So if,
No, I still
yeah,
don't
if
understand.
xy, does it make sense? So if xy
No.
wasn't in my polynomial, if xy wasn't in my polynomial, so this vertex is not in the, you know, in the polytope. So my polytope would be just this guy, excluding this red point.
So there wouldn't be any red point at all.
Yeah, there wouldn't be like
Would
any.
there be a red point with no edges, or would there be no red point?
So like in the example that we are talking, so there would be no red point and no edges. Okay,
Sure.
so that would be just this triangle. But I'm looking at the intersection with Z2. So that means when I'm looking at the intersection, I would like to add, to include like all those lattice points. So there would be, or, you know, let me just say, like,
Oh.
would be this point, but not connected, right? So I mean, this point would be like in the interior of your polytope, but without, you know, any edge attached to it.
Okay.
Okay, so of course, you know, the polytope contains this point, but what I'm saying is you won't see it like as a, you know, as a vertex in the subdivision, right? Okay, good. So, so what I wanted to say here is that, you know, you have this tropical point, you have these tropical curves, and then you look at the corresponding subdivided picture, and this combinatorial picture, which is just a polytope, encodes a lot of information about this curve as well, right? And that was just one example of the genus. So, okay, so let me tell you just maybe one more example that, you know, how the classical theorem would be translated to the tropical version. So like in the classical algebraic geometry, you might have two algebraic planar curves of degree d and d prime. So that means there are two polynomials like f of degree d, and g of degree d prime. So like in two variables x and y, okay? So, and then you would draw the corresponding curve of these two polynomials. So, and then there is a Bezout theorem in algebraic geometry saying that these two planar curves would intersect in d times d prime points. Okay, what is an example of such theorem? If you have two lines that they are corresponding to degree 1, each of them is a degree 1 polynomial, right? So there's a linear form. So if you have these two lines, every two lines intersect like in a point, like generic, right? So I'm not, of course, counting if I have two parallel lines. So I would say they intersect like in infinity. Okay, so like every two generic lines, they intersect like in one point. And if you have like a curve of degree 2 and line, so one of them is of degree 2, the other one is of degree 1, so then they would intersect in 1 times 2 point. And of course you would have, again, you know, this degree 2 curve and then one line which is kind of attached to it, right? Which is touching this curve. And then here you see just 1 point, but actually you can count it with multiplicity 2. Right, so these things are known like in algebraic geometry that you have, again, you count the number of intersection points as 2 because in these specific examples, right? And then you want to see what is the tropical version of Bezout's theorem. In a sense, you know, you want to ask, if I look at the tropicalization of these curves, can I say the same statement? Can I see the number, can I count the number of intersection points? Oh, okay, let's look at here. So I have two lines, and then I look at the two tropical lines, and then you see that, you know, if they are in a generic position, so they intersect in 1 point, right? And then here by generic, I mean, so they only intersect like in finitely many points. For example, you know, I mean, these two lines, these two rays are not coinciding somehow. So then you would have one intersection point. So like in this picture, you said, you know, I have a tropical line drawn in blue, and I have this tropical curve of degree 2. And I see the degree because I can see the number of rays here, which is 2. And again, they intersect like in 2 points. Okay, but I also see this third picture, which is like a line and also a curve of degree 2, and I see that they intersect in only one point. Okay, so this is somehow the same kind of property, the same structure that I would see here, but then here it was kind of clear that there is a multiplicity 2 intersection point, but from this picture, so it's not clear, you know, how to count this multiplicity, how to count this number of intersection point, which we can see is just 1 as a 2 intersection point. Okay, so the goal would be to provide, I mean, somehow like in tropical geometry, so the goal is to provide a simpler model of algebraic geometry. So here the question would be why some of these intersection points are counted twice, like this picture, and then we want to translate it again in terms of, you know, some combinatorial data of these subdivided polytopes. So, and then, you know, as I said, so I take this generic case, and by that, I mean the curves only intersect like infinitely many points. And okay, so now if I look at these curves, so each of them actually can be, I mean, this is the union of two curves, but I can see it as the curve of the tropicalization of this product. So I can think of, you know, this guy as just one curve, which is corresponding to the product of both of them. Okay, so that means whenever I have such a picture, so I can draw its corresponding subdivided polytope. So how do I do that? So I start from this, you know, this picture, and then play the same game, you know, looking at the coefficients of this polynomial, lift the corresponding Newton polytope to one dimension higher, and then project it back, and then you see these sort of like subdivided pictures. Okay. And the observation here is that if I look at these guys, okay, if I look at these guys, so these intersection, I can see that, you know, each intersection point, I mean, there is a duality, right? So like each intersection point here corresponds to like such a parallelogram. Okay. So like I have a square here corresponding to this intersection point. Because, you know, the red curve somehow like gives me this red triangle as a dual. So the blue curve gives me this blue triangle here. And then this intersection point corresponds to this square that I see here. Okay, and then this is the same for all of them, for all the other curves. And the observation was that the area of these you know, foregons that I see here are dual to the intersection points, and the area is really the area of these foregons that they are dual to the intersection points are related to the multiplicity of these intersection points. For example, here, you know, I said these are just the unit triangles, right? So this was just 1 times 1. This area is 1. This area is 2. Right, this area is 1, etc. And then I see that this intersection, the area is related, like in a sense that here, you know, so I have 4 of these small triangles, so I would get 2, and this 2 is exactly the multiplicity of that intersection points, like in the tropical picture. So it turns out to be true that, okay, so here again, you know, I'm looking at my specific examples of 2 lines. Okay, and that was the 2 lines intersecting in one point. And then when you look at the dual picture, so I have a square of length 1 times 1. So that's the area and the multiplicity. And it turns out that this is exactly the, you know, tropical Bezout theorem, that for every intersection point, you can look at the corresponding, the area of the corresponding foregon. And then if you sum up all these areas for all the intersection point, you get exactly d times d prime, you know, as this number, which was corresponding to the number of intersection point in the classical algebraic geometry. Okay, so here, you know, as we saw, so there were like 2 intersection points. Each of these guys has area 1. So it would sum up to 1 plus 1, which was 2 number of these guys. And then in the other picture, so I had this 1 intersection point corresponding to the foreground of, whose area is 2. So that was the multiplicity of this point. Okay, so I wanted to tell you the proof, but I think I'm going to stop here because we are already, I'm already over time.
Question?
Okay,
Is
maybe
there
ask for a question. Yeah.
in the primal picture, is it easy to spot geometrically the meaning of a multiplicity, or only in the dual picture?
Oh, so like in the original one? Yeah,
in the bottom left.
Yes.
That's the upper left, bottom left. Go down to the left, go to the left. There, yes. Is there something geometric happening there that I can see that's a multiplicity?
I mean, this is just the tropical picture, right? So you would
Yes.
see like in the, so you would say like in the original picture, right?
No,
so
I'm not looking,
like,
I want to look at the tropical picture.
So like in the tropical picture, no. So it's not, I wouldn't say it here.
Got it.
But then that's why we go to the subdivided picture, because then we would say like as a, as the area of the triangle.
Thanks.
Yeah, sure. So is there any other question? Please unmute yourself and let me know.
I had a question in the, I put it in the chat. My question was just that on the left, you have a non-generic setting, right? So you have a parabola with a line that just intersects once. Do you see any indication of that, I guess, non-genericity in the tropical curve? Like, can you tell that it comes from a non-generic situation?
Oh, you mean here? What do we mean by non-generic situation?
Oh, so maybe I'm wrong, but I was just assuming that this would be non-generic because the line intersects the parabola just once, right?
Mm-hmm.
Is that
So now by generic, I mean in the, like in this setting, like in the classical setting, I don't want to have just one intersection point. Like non-generic here would be just, if I have such a line intersecting it like in one point, but then when it's touching somehow like the space, so you would count it like as with multiplicity 2 in algebraic geometry, right?
Yeah. Okay. So is that line drawn as tangent to the parabola?
Yeah, exactly. So that's what I mean. When it's tangent, so you would consider the multiplicity, but the non-generic case, like in the classical setting, would be I have such a line that would intersect my curve in just one point.
Okay.
Yes. And then here somehow like you see the, it's kind of easier to see the this non-genericity, but not in this picture, right? Because here I define exactly, because here I define non-generic setting, like in a sense that you don't have two rays overlapping, or you're kind of away from these points like in the middle.
Okay, because I noticed on the next slide there was an isolated point in the or
here?
where no, there was when we were looking at I think the projection. Oh,
you mean here?
No, so there were 3. Where was it? Yeah, there. So on the left, there was that isolated point. I didn't know if that would happen whenever you have like a weird, intersection, like a tangency or something like that.
Also, these points are just lattice points of this polytope, right? That's what I mean. So it doesn't mean that so when I put these points, I just draw the such a lattice, all the lattice points of this triangle. It doesn't mean that this point is actually on my curve. So by drawing this point, I don't mean saying that, x, y was a term like in my polynomial, in my tropical polynomial.
Okay, I see. Thanks.
Yeah, that by the way, that really confused me, because you have different kinds of drawings, but you don't distinguish them. One drawing is your projected Newton polytope, and the other drawing is the entire lattice. So you
Yes,
should be careful
now
about
I
it.
understand the confusion. Yeah, now I understand the confusion. So like what all I mean is, all I'm drawing here is all the lattice points, but they don't mean that they are coming from the terms of my polytope. Yeah, now I understand your point. Fair enough, yeah.
Can you say just again how you compute the area of this large square?
Yes, so so whenever I have a line, so just one, okay, let me go back here. So whenever I have such a line, so I consider this kind of small triangle corresponding to this line. Okay, and the triangle has been drawn such that like every edge has length 1, right? So the area of the triangle, small triangle, would be half 1 divided by 2. So now, whenever I have like degree d, like here I have what is like here, when I have 2 curves, I have degree 2. Okay, so then I would look at the big triangle, which in which the length of each edge is 2. So this is just 1 times 1. So that would be the area of my of this square. And then here the area is half and then half again. And the total area is 2 times 2 divided by 2.
So on the left, we really are supposed to think of this square as a √2 by √2 square.
Exactly. Exactly.
Okay, great, thanks.
Yes.
Could we also flip to the last slide?
Yes. This one?
Maybe the proof.
Oh, the proof. Okay. So you want to tell me, you want me to tell you like a little bit about the proof?
Sure, yeah.
So like in the proof, okay, so what was the statement? So I started from 2 polynomials f and g, okay? So their corresponding curves are of degree d and d prime. And the statement is that, these 2 tropical curves, if you count this multiplicity by looking at the area of the polygon corresponding to this intersection point, so, this sum of these multiplicities would be just this d times d prime.
Mm-hmm.
Okay, so and then, or would you like me to tell you about the statement or the proof? Sorry, I wasn't sure what you asked.
I was curious about the proof itself, but
Okay, the proof.
Yeah.
Okay, sure. So okay, so the the corresponding. So we just said whenever you have 2 polynomials and then you're kind of looking at the union of their curves. So that curve would be corresponding to the degree d plus d prime polynomial, which is actually the tropicalization of the f times g. Okay, so that means if I have this tropicalization of f times g, so that's a degree d plus d prime curve. So if I want to look at the dual, this subdivided, this Newton polytope, so then I have to draw like a triangle whose edges are of length d plus d prime. Okay. So, and then the sum of all these areas, so that's a this triangle. So the sum of the area should be this number, which is d plus d prime squared divided by 2. So now I look at all the regions, all the polygons in my subdivided picture. So there are 3 types. So either they are these red polygons that they are corresponding to the vertices of my, my curve coming from F. And I know what is the area of these what is the sum of these areas. That would be just d. That would be corresponding to this d delta, which is d square half. And then I know I can, sum up the area of those blue polygons. That would be the area of d prime delta. And then I also have the sum, the area of this big triangle. So if I subtract these 2, so then what I get is just this d prime, which is the area of those bicolored polygons that they are corresponding to the intersection points.
Nice.
Yeah, so it's really like a combinatorial proof. Once you have the right definition for the multiplicity, so what is left is, the proof is really easy then.